All right, this is section 4.6, applied optimization problems. So when we do these, they're obviously going to be word problems, and we need to focus on what the goal is. If it's applied optimization problems, that means we're going to either maximize or minimize an applied quantity. Okay, so basically we're going to have to find an equation. We're going to have to take that derivative of that equation, set it equal to 0, and then figure out if it's a max or a min. So the first step in doing these problems is you're going to write the quantities you're trying to max or min as a function of one of the other variables. Sometimes this step is going to require you to have two different equations, kind of like the problems we did before. And that way, if you have two equations, you can figure out what one of the variables is by just using a little bit of algebra. To do this, we have to understand what quantities are given and which we need to be assigned variables. When feasible, make a sketch and label all measurements with a variable or constant. We also need to write an equation for the quantities that it is to be maximized or min. Part C, use substitution so that the quantity to be maximized or minimized is written as a function of one other variable. And that's what I was talking about. We usually will have two different equations, and we use one of those equations so that the way we can write the variable as a function of the other. And the last step is to determine a feasible domain for the function. Part 2, we're going to find the derivative and critical points. So take the first derivative once we have that equation written out, and then set it equal to 0, or find where it's undefined. And then prove your critical point generates an absolute max or min. You can do this by either using the closed interval method, or you can, if it's an open domain, you can use the first or second derivative test to find the local extrema. Basically, we can do that if f of x is continuous on the intervals from a to b, and f at the critical point is the only local max or min, okay? So let's go ahead and look at example number 1. A rectangular pen bordering a river is to be made from 900 feet of fencing material. The pen is to be divided into two sections as shown in the diagram. What is the maximum possible area of the pen? What dimensions will give the area? So the problem's asking us to maximize area. Okay, so we want to maximize the area. So if I look at that little diagram, I'm going to say, if this is a rectangular pen, let's say that the length of the vertical sections are x because they're all the same. And then let's call the width y. And I know the area of a rectangle. The area of a rectangle I find by taking length times width. Okay? So if the length is y, and then the width is, if we, multiply this together, we get 3x. That's, or add them together rather, we're going to have an issue here. So let's go ahead and figure out if we can figure out another equation that we can use so we can write up, y in terms of x. So if I looked at the diagram, I basically have this situation going on here. I have x, 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 and I know we have y, the width. I know that there's 900 feet of fencing. So what I can do is I can find the perimeter of this fence. Or actually, when I say the perimeter, actually how much fencing we're using, right? So if I have the length of x, x, and x, I can put x plus x plus x. That's going to be some of the fencing. And then I'm going to add in y, right? And this is going to equal 900. By the way, I didn't include the top because remember the top was right by the water. So that part's, kind of fenced in on its own. So if we add those together, I get 3x plus y equals 900. And then if I just rearrange the problem a little bit, I can say that y equals 900 minus 3x. Now I have my equation so that I have y equals something in terms of x. So if I go back to area, remember area equals length times width. And I know that the length is x, right? And then the width, the y portion, is now 900 minus 3x. So now I have my equation in one variable. And to do this a little bit more, I get 900x minus 3x squared. I know there's no place in which this function is going to be undefined. I also have limitations that the fencing has to be a value between 0, and it has to be actually greater than 0, because that means no fence at all, right? So the fencing has to be greater than 0 and less than 900. Okay, so those are my stipulations. So I have like, an open interval, if you will. All right, so I have my function. Remember, I'm trying to find the maximum amount of fencing I can use to enclose this pen. So what I'm going to do is I'm going to take the derivative of the area function. So if I take the derivative of this, it's going to be 900 minus 6x. Okay? The next step I'm going to do is I'm going to set that equal to 0. So 900 minus 6x equals 0. Negative 6x equals negative 900. X equals negative 900 over negative 6. So go ahead and, pause me for a second, figure that out, and we can check with each other. But when you do that, I got x equals 150. Okay, so remember, that's going to be my critical point. You can do one of two things. You can make the chart. We can do that, or you can take the second derivative and find out if you have concave up or concave down. The second derivative is actually not too bad, so if you want to do it that way, you can. Or if you want to use the test point. So, since we just got done with the test, if I use my test point method, I could put 150 here, right? And then remember, you use your test point, you check it in your first derivative. For instance, 0 on the left-hand side. And then I'm going to figure out if it's plus or minus. And then the next step is figuring out if the function is increasing or decreasing, okay? So I am going to use a test point of 0. Let's use a different color. So test point 0 on the left. And on the right, let's use 200, okay? So remember, I'm plugging this into the first derivative. So the first derivative, remember, if I plug in 0, the first derivative is 900 minus 6 times 0. That's 900. That's positive. So I know my function is increasing. Now, if I take the first derivative at 200, I plug it in, so I get 900 minus 6 times 200. Well, 6 times 200 is 1200. So I get a negative here. So I know my function is decreasing. When that happens, you put these pieces together, you've got a max at 150. So we can conclude that that is the maximum. That's what x equals, So x is 150, but it's asking us, what's the dimensions? So remember, x is going to be the width, right? So now I have to find the length. To find the length, I'm going to plug in 150 into the original equation. And remember, our original equation was 900 minus 3x squared. So we can do 900 times 150 minus 3 times 150 squared. That's one way to do it. Or, I can use this equation, which might be a little bit faster, guys. A 900 minus 3x. So, I'm going to actually go for this one. So 900 minus 3 times 150. 150 double is 300, so I get 450. So this is going to be 900 minus 450, which is going to give me 450. Sorry, I almost put 350 down there. So this equals 450. Okay. So if my width is 150, my length is going to be 450 feet. Okay, so those are my two values for this problem. Those are my answers. So let me just make a box in yellow so you know that that's the answers. Okay, all right, so once again, you can use some of the skills we've learned to find out where something is a max or a min.